Okay, so we're starting lesson 2.2, talking about the integrated rate law. So the integrated rate law describes the relationship between concentration of reactant and time. Concentration and time. So remember the rate originally, we just had the initial concentrations and the initial rate. Now we're talking about how does the concentration change over time. So first off, we're looking at a zero order reaction. So zero order reaction. Consider this reaction. We have substance A becoming products. And the rate law for this zero order reaction is rate equals K times the concentration of A to the 0 power. This is a zero order reaction. This is how we know it's a zero order reaction from the rate law. So as the concentration of A decreases, the rate or slope, let's draw this thing. So off to the right you have this, it says concentration of A versus time. So what's going to happen is no matter what, time is going to move on. So our graph is continually moving to the right. And so here's what happens in a zero order reaction. So let's say that we start with this amount of the concentration of A initially. In a zero order reaction, looking at a concentration versus time graph, it just decreases constantly and time is moving on. And this graph is a straight line. Do a little bit. Okay, so here's what's going on. As the concentration of A decreases, the slope is constant. It's a straight line. So a graph in which the slope is constant is a straight line. Therefore, the rate equals the slope. So let's write this. Rate equals the slope. And up here, the slope equals negative, say negative K. So negative K, and the reason it's negative because A is being used up in the reaction. So write the equation of the graph in slope-intercept form, y equals mx plus b. All right, so let's duplicate this page. Okay, so in y equals mx plus b format, your standard math formula for a straight line. This is what the integrated rate law looks like. And I don't want to do a lot of deriving formulas. Here's what it looks like. Your y is the concentration of A. And your slope is negative K. Your x value is time. And your y-intercept is at this point right here. And this point is what we call the concentration of A at time 0, or the initial concentration. So plus the initial concentration of A. So this is how we come up with this formula. It's just a straight line. And a lot of times this y is called A sub t, just the concentration of A at whatever time we're talking about. Typically, you'll see this formula rearranged, and it's going to look more like this. So the concentration of A at some point in time, subtract over the initial concentration, equals negative kT. So this is the formula that you'll typically see, and it didn't used to be on the AP formula sheet, but as of 2020, it is on the formula sheet. The formula sheet that I gave you in class is 2019, and so this one is not on there, but it is on the 2020 and hopefully future. You just have to know that this is first order. So let me write down what these things are so we don't forget what they are. A sub 0 is initial concentration. A sub t equals concentration at time t. So all of this is for the 0 order reaction. And I wrote first order, I shouldn't have done that. Go back and look at this. And it is a 0 order reaction, not first order. 0 order, this is the formula, and yes, it should be on the formula sheet this next year. Okay, so now we're moving into a first order reaction. All right, so for a first order reaction, we have the same type of reaction. We have A yielding products. So we have one reactant turning into some products. And we have a new rate law given to us. The rate law is rate equals K times the concentration of A to the first power. And this is how we know that it's first order, because our exponent is 1. So as the concentration of A decreases, the slope decreases. As the rate gets slower, the slope gets smaller. So let's write this down. As the rate gets slower, the slope gets smaller. And so we get a curve. So here's what it's going to look like. So here's my initial concentration for A. And so what happens is the reaction starts off really fast, and the rate starts to slow down And so you can see this reaction is slowing down, and eventually kind of levels off, something like this. So if you're looking at it in terms of slope at any one given point, right here, the change in concentration versus time is very fast. So the rate here, the slope, look at how steep the slope is. So let's not draw that. We don't want to cloud up our picture here. But if you look down lower, the slope, the tangent line at this point is not nearly as steep. And once we even get further, the tangent line is here. So as the rate slows down, the slope is getting smaller, and so we end up with this curve like we're seeing here. Unlike the zero order reaction, the concentration versus time graph is not very useful. So not useful because it's not a straight line. So it's not useful for analysis. I once had a chemistry teacher tell me, curves tell us nothing. Straight lines give us useful information, but curves tell us nothing. So for the first order reaction, we get a linear relationship if we change the graph. So let me clear some of this up, and we're going to draw a different graph. This time we are looking at the natural log of the concentration of A versus time. There are circumstances where we can take our concentrations and find the natural log of each of them and plot it. But right now, for the basis of it, I'm just going to draw you what the graph should look like. For a first order reaction, we get a linear relationship between the natural log and time. And so we have, starting up at the top, here's the natural log of the concentration of A, and we end up with a graph that looks like this. And so we have the slope. It's a negative slope because it's being used up. And so this is helpful. So again, if we're going to put this in the formula for a line, it would look something like this. The natural log of the concentration of A, because that's our y-axis, that's where this is coming from, equals, slope is negative k, x-axis, the x is still time, so there's t, plus our y-intercept, which is b, is the natural log of the concentration of A at time 0. So right here is the natural log of concentration of A at time 0. Just like the other formula, it's usually written a little bit differently on the AP formula sheet or in other formula sheets, wherever you encounter it. And what they do is they subtract this one to the other side. So we have the natural log of the concentration of A at time t. So that's what this one would be. Equals, not equals, minus the natural log of the concentration of A at time 0, equals negative KT. And so this is the formula that we use for a first order reaction. This one is a first order reaction. Same things as last time. Concentration of A0 is initial concentration. Concentration of A sub T is concentration at time of T. So this one is on the AP formula sheet. It's not labeled first order, but as long as you can look at it and identify it from three different equations, the natural log equation is the first order reaction. So the next idea we have is the half-life. So the half-life, or in symbols, T sub 1/2, T1/2, is the time it takes for a reaction to reach half of its original concentration. So if I were going to look at this graph again, actually not this one, the graph that looks like this, where it's concentration versus time. Here is the initial, and let's say this is the halfway point, so we draw it over. This is the amount of time that it takes. So if you use the integrated rate law for the first order reaction, you can solve for the half-life if the concentration of A equals 1/2 the concentration of the initial concentration. Yeah, this is kind of a lot. And it says it's not on the AP formula sheet. Actually, it is, excuse me. So let's not spend a lot of time trying to derive a formula here. What it is, the half-life equals 0.693 divided by K. And really what this means is, this is how we got it. T1/2 equals the ln of 2 divided by K. But this is the one that's on your AP formula sheet, and it's a fairly simple formula. Just make sure you look it up. All right, so now we are on to the next page. And we're going to look at a second order reaction. So, looking at a second order reaction, and we have two graphs again. We have one that is concentration versus time. And then we have another graph that we're going to use in a minute. So we're still talking about a reaction where substance A is yielding products. And the rate law for this reaction is rate equals K times the concentration of A to the second power. And this is how we know that it's a second order reaction. So here's what happens as the concentration of A decreases, the rate or the slope also decreases. And so our concentration versus time graph looks something like this. And same idea as last time. As the rate gets slower, the slope gets smaller. So we get a curve. Again, curves are not really useful in chemistry, and so this graph is really not going to tell us anything. Curves tell us nothing. So again, unlike the zero order reaction, concentration versus time is not very useful because it's not a straight line. It's not a straight line, so it's not useful for analysis. But we can alter our data, or not alter it so much as just use our numbers differently. Instead of the graph of the concentration of A, we can use 1 over the concentration of A versus time. And what we end up with is a graph that looks something like this, where the slope equals a positive K. So this is a linear relationship, and now it's got a positive slope, and that's how one of the ways we could know it's second order. Putting it into our y equals mx plus b format, your y is 1 over the concentration of A. So let's write it like this, 1 over the concentration of A equals my slope is positive K, my x is time, t, and b, my y-intercept, is 1 over the initial concentration of A. So right here, 1 over the initial concentration of A. Like all of the others, the y-intercept gets subtracted to the other side to make the formula that we find on the AP formula sheet. So 1 over the concentration of A, and this is at whatever time t, minus 1 over the concentration of A times 0, the initial concentration, equals positive K times time. And this is the formula that you'll see for a second order reaction on the AP formula sheet. Remember, the slope here is positive, and So that's going to be an important piece of information. Actually, on your formula sheet, I'm looking at it now, and they don't have the positive written, but when there's no sign, positive is applied. So it's a positive slope. Okay, so the last part about this, the half-life of a second order reaction. Again, I don't want to get into deriving equations and making this more difficult than it needs to be. The half-life for a second order reaction is 1 over K times the concentration of the initial. But this was not on the AP formula sheet. And so we're just going to leave it at that. You can write it down in the notes, but just know that the half-life, this is the one that is on the AP formula sheet. And this was for a first order reaction.